Okay, we are talking about the sticking coefficient, and we find that for gallium arsenide growth, the sticking coefficient of gallium is unity below 480. That means, if you grow at 480 degrees centigrade or less than that, the gallium arsenide sticking coefficient is 1. Okay. Now, if you grow above 480 degree centigrade, you will find that it is less than 1. Less than 1 means, depending on the temperature, it can be 0.5, 0.6, 0.7, 0.8, 0.9, etc. That means, it has very good sticking coefficient, and arsenic sticks only when a gallium adatom plane is already established. Okay. Now, the growth rate of 3,5 compounds is entirely controlled by the flux densities of group 3 beams Fi. That means, gallium arsenide, indium phosphide, indium arsenide, indium gallium phosphide, all 3,5 compounds, the growth rate Rg you find that is a summation of alpha I S Fi. What is I? I is the number of different group 3 elements, okay, and F is the flux. Flux, that means which are coming out from the oven or the effusion cell, that flux. Now, growth rate is proportional to this, means suppose I want to grow indium gallium arsenide. In that case, Rg will be proportional to what? Rg will be proportional to the sticking coefficient of indium multiplied by the flux of indium plus sticking coefficient of gallium multiplied by the flux of gallium. So, that is the meaning of this summation. That is the meaning of the summation. Alpha is the sticking coefficient and F is the flux, and they are basically the group 3 elements. So, if I would like to grow indium gallium arsenide, here group 3 elements are indium and gallium. So, the sticking coefficient of indium multiplied by the flux of indium plus the sticking coefficient of gallium multiplied by the flux of gallium. So, arsenic has no role basically in the growth of indium gallium arsenide so far as the growth rate is concerned. Arsenic cannot change the growth rate. Growth rate will be governed by the 3 group elements. Say, let us take another example of aluminum gallium arsenide. The growth rate will be proportional to sticking coefficient of aluminum multiplied by the flux of aluminum plus the sticking coefficient of gallium multiplied by the flux of gallium. That is all. Arsenic or phosphorus or antimony has no role to determine the growth rate of the 3,5 compound. Growth rate, remember, it is required, otherwise no growth will take place, but it has no role so far as the rate is concerned. For aluminum gallium arsenide growth, we have separate effusion ovens made of pyrolytic boron nitride for gallium, aluminum, arsenic and the dopants. What are the dopants? The dopants are silicon or sulfur for N type and zinc for P type or beryllium for P type. All the effusion ovens are housed in an ultra high vacuum chamber that we have seen. The temperature of each oven is adjusted to give the desired evaporation rate, because element to element there will be variation so far as the evaporation rate is concerned. You cannot evaporate gallium using the same temperature which you have used for indium or aluminum. If for aluminum it is T1, then for indium it will be T2, for gallium it will be T3. And substrate holder rotates continuously to achieve uniform epitaxial layers. It is continuously rotated, so that the growth becomes uniform in all directions. Now, the most important thing in MB growth is the molecular impingement. What is impingement? Impingement rate is how many molecules impinge on a unit area of the substrate per unit time. Remember that, per unit area per unit time. How many molecules impinge? Impinge means fall. Impinge means fall. It comes in contact with the substrate. Okay. So, that is very important, and that is given by phi equals to p 2 pi m k T to the power minus half. What is P? P is the pressure in Pascal, T is the temperature in Kelvin, K is the Boltzmann constant in Joule per Kelvin, and small m is the mass of a molecule in kg. So, this is the molecular impingement rate, that means how many molecules impinge on a unit area of the substrate per unit time. Now, this impingement rate we can calculate obviously. Then the rate, if you change with the capital M, that means the molecular weight, it is not a molecular weight, see that it is the mass of a molecule in kg, that is small m. Okay. That we want to convert into capital M, that means the molecular weight of the atom. So, it comes out to be P by root over of MT 2.64 into 10 to the power 20. How it comes? Pi is there, K is there, and you can convert it to, if you put the value of the K etc., it comes out to be 2.64 into 10 to the power 20 into P by root MT molecules per centimeter square second. That means per unit area per unit time, the number of molecules, and capital M is the molecular weight, T is the temperature in Kelvin, and P is the pressure in Pascal. So, that is the molecular impingement rate, which is very important. Now, you calculate at 300 K the molecular diameter of oxygen is 3.64 angstrom, and the number of molecules per unit area is 7.54 into 10 to the power 14 centimeter square inverse. Find the time to form a monolayer of oxygen at pressures of 1, 10 to the power minus 4 and 10 to the power minus 8 Pascal. Okay, what we want to know, the time to form a monolayer of oxygen, and for monolayer it is given that 7.54 into 10 to the power 14 per centimeter square molecules are required. Okay. And diameter of the oxygen molecule is given. Remember that the diameter we need not to use, because if you use this expression, what is required? You require the temperature and M, molecular weight and temperature. Since it is 300 K, that is the temperature fixed, molecular weight it is oxygen, you know, because the pressure is varied. First the pressure is 1 Pascal, then 10 to the power minus 4 Pascal, then 10 to the power minus 8 Pascal. Okay. So, you try to solve this numerical problem, that is very important problem to understand that how the pressure determines the growth. Phi is 2.64 10 to the power 20 P by root MT. What is M for oxygen? 32, and temperature T is 300 K. So, you put 32 multiplied by 300 root over of, keep P as it is, because then with that expression you have to put P 1, 10 to the power 4 and 10 to the power minus 8. Then what should be the result? You will find that so far as this is concerned, I can show you the result. Say phi is equals to how much? 2.64 into 10 to the power 20 P by root over of m t. So, now you put m and t, then tell me what is the value. You just put m and t and tell me what is the value. If m is 32 and t is 300 k, then what is the value? What is 8.6 into 10 to the power 19 multiplied by p, multiplied by p. Then time, because in this example you see that find the time to form a monolayer, find the time to form a monolayer. So, time is t equals to ns by phi. Ns is given, number of molecules per unit area 7.54 into 10 to the power 14. Okay. So, if you take this value, Ns is 7.54 into 10 to the power 14 by phi is 8.6 into 10 to the power 19 p. Okay. For 1 Pascal of pressure, T will be 0.28 millisecond. You can calculate in your home and you will find that T is 0.28 millisecond. For 10 to the power minus 4 Pascal, it is 2.8 second, and for 10 to the power minus 8 Pascal, it is 7.7 hour. So, what we find? We find that as the pressure increases, since the time is inversely proportional to the pressure, time goes up, that means from 0.28 millisecond to 7.7 hour. Okay. So, you find that the growth rate is very slow, growth rate is very less, 7.7 hour from 0.28 millisecond. But do not try to grow the epitaxial layer using 1 Pascal of pressure. In MBE, minimum 10 to the power minus 8 Pascal is required, because ultra high vacuum conditions must be achieved. Okay. So, even that here 0.28 millisecond or 2.8 second is required for that kind of a growth, but the growth will not be a good one, because you are not achieving the ultra high vacuum condition. What?
This 8.6 is not there, it should be 2.69 into 10 to the power 18.
2.69
into 10 to the power 18.
10 to the power 18. Okay, it is immaterial, because you can always check. The absolute value is not important for us. For us, the important factor is that as we go on increasing the vacuum, the time increases. That is the main theme, that you can check from in your home, that is not a major problem. Okay. Now, the second important factor is the mean free path. So, that is very important, that the mean free path problem is very important, and you see that this, so far as the mean free path is concerned, lambda is the mean free path, it is given by k t by root 2 pi p d square. What is k? K is Boltzmann constant, T is the temperature in Kelvin, P is the pressure in Pascal, and D is the molecular diameter. Okay. D is the molecular diameter. This is a very important parameter for MB growth, that the mean free path must be as large as possible to avoid any collision from the effusion oven to the substrate, because from the orifice of the effusion oven to the substrate, the molecules must traverse a distance, finite distance, that is a finite distance, and it must not be suffering from any collision. Here also you see that so far as the mean free path expression is concerned, this P is in the denominator. P is in the denominator means to increase lambda, P must be small, means 10 to the power minus 8, minus 9, minus 7, that type of thing. From 1 to P is 1, say atmospheric, so it must be 10 to the power minus 8, so that lambda will increase manifold. Now, how this mean free path is calculated? How this mean free path is calculated? This mean free path is calculated using the concept of this kind of a modeling. You see that there is a atom of diameter d. So, it will collide with another atom, because say these two atoms are there. So, any atom which are coming within this range of 2d diameter will be scattered. This is one atom of diameter d, and this is another atom of diameter d. So, the total diameter of this system is 2d. So, this 2d is the new diameter of a theoretical sphere, which will move say up to the distance of x in time t. This can move. So, any atom or any species within that area will be scattered by these molecules or atoms. So, that is the model. That means, this area will be pi d square. Okay. This area will be pi d square, and if this is if the velocity is v bar and time is t, so the distance is v bar into t. So, multiplied by v bar t, so that is the volume. So, mean free path will be this distance by pi d square v bar t multiplied by n v. N v is number of molecules per unit volume. N v is the number of molecules per unit volume. Say it is a consider the kinetic theory of gas. Consider the kinetic theory of gas. All molecules are moving and they are colliding with each other. So, if I consider a time t and the molecules move with a velocity of v bar, then at time t it will cross a distance of v bar into t. So, that is the distance, and number of scattering will be n v is the total number of molecules per volume. What is the volume? Volume is this. Volume is this. So, if you multiply this volume with the number of molecules per volume, so within that volume the total number of molecules will be pi d square v bar t multiplied by n v, and if you divide v bar t with this thing, you will get what is the value? the value is obviously value of lambda will be 1 by pi d square into n v, 1 by pi d square into n v, okay, because you see that this is v bar t cancels out. So, 1 by pi d square into n v. But you see that here we have used a different kind of expression which is given by k t by root 2 pi p d square. So, from this expression we have to come to that expression. Here you see that the mean free path is related to the molecular movement. Now, what is this v? This v bar is basically you must take the relative velocity of the molecules. Why? Because no molecule is in stationary state, all the molecules are moving. So, when I talk about this v bar t, that v bar t is not the actual v bar, it is basically the relative velocity we have to consider, and that relative velocity is basically root 2 of v. Okay. V bar root 2 will be the relative velocity REL, that you can prove. In the textbook you have already proved in your BSc classes. The relative velocity is basically root 2 v. So, now the lambda becomes 1 by root 2 pi d square n a p multiplied by r t. How? Because what is n v? N v is equals to n into n a by v. How? From Avogadro's hypothesis. N v is small n multiplied by n a by v, and that is equals to n into n a by v equals to n r t by p. P v equals to n r t. This is equals to n a p by r t. So, if you put n v here, you will get this expression. R by, yes, R by n a equals to k. So, this R by n a equals to k. So, lambda is equals to k t by root 2 pi p d square. I will not ask you in the exam to deduce it, just I am giving you the confidence that the expressions are true, and it is not very complicated thing. It comes from mainly the kinetic theory of gas, so using some Avogadro's hypothesis and related equations that you can consider. Okay, so, that is the thing, and you find that lambda is k t by root 2 pi p d square for air molecules. What is d? D is 3.7 angstrom. It is 3.7 angstrom. Then what should be the value of lambda? If you put the values of k, t, d, t is 300 k, k is 1.38 into 10 to the power minus joule per Kelvin. So, if you put, you will find that lambda equals to 0.66 by p in Pascal, that much centimeter. That means, in this expression I have put the value of k, then t, then root 2 pi, then d square, d is 3.7 angstrom, this is for air molecules, then lambda become this Pascal. Okay. So, when p equals to 10 to the power minus 8 Pascal, what is the lambda? What is the value? Tell me in kilometer. Tell me the value in kilometer. What is the value of lambda in kilometer? Yes, around 660 kilometer. So, that means what you find? That the mean free path for air molecule at room temperature with a pressure of 10 to the power minus 8 Pascal is very, very high. That means it is 660 kilometer. What it means? What is the physical implication of this? Yes, two air molecules will collide after 660 kilometer, not before 660 kilometer. So, that means 660 kilometer is free space, free from any collision, it is free space, free from any collision. So, that is very important thing, that the pressure must be very, very high. Under such a situation, not that you will avoid the collision, at the same time you will avoid contamination. All other remnant gases which are in the gaseous form, in the vapor form, they will leave. The most of the problem is created by oxygen, it forms oxide. So, oxygen is evacuated. Okay. So, you see that this high lambda, because of the high lambda, to achieve 10 to the power minus 8 Pascal of evacuation is required. Here this is one example of an ideal gas at STP, that means at 0 degree centigrade and 760 millimeter of mercury pressure. The values are, you see, that is an example only. This is a molecule of an ideal gas, its diameter is 0.3 nanometer diameter, and average molecular separation is 3.3 nanometer. Its mean free path you see 93 nanometer. 93 nanometer means it is 28 times the average molecular separation and 310 times the nominal atomic diameter. It is very, very high basically. Mean free path is the free space travelled by the molecule before successive collisions. Between two collisions, how much it can move without any collision. And you see that so far as the atomic dimension of the atoms and molecules are concerned, it is very high, because if the atomic diameter is 0.3 nanometer and if it is 93 nanometer the mean free path, then mean free path is very, very high than the atomic diameter, and it is, you see, there is 310 times in this case, not a matter of joke, 310 times. The red line shows that this atom will collide with this atom after 93 nanometer. So, this is a model basically with some specific values, and this is very important concept in an MB growth. Here you see that the atoms, this blue are the arsenic atoms, then green are the gallium atoms, and this is layer by layer growth you see. This is one layer, this is second layer, then the third layer is being grown. So, this is one monolayer, this is second monolayer, this is third monolayer, but it is not complete. Okay. So, such type of thing is going to happen in MBE. First, the atoms arriving at the substrate surface will undergo adsorption to the surface, that means they will accumulate on the surface. Then there will be surface migration, say from point A to point B or point B to point C. Incorporation into the crystal lattice means on the substrate. Then there will be thermal desorption and depends strongly on the temperature of the substrate. One thing is missing with the vacuum of the system also, it depends strongly, because we have seen that the growth rate is 7.7 hours was required for 10 to the power minus 8 Pascal, whereas for 10 to the power minus 4 Pascal the time required was 2.8 second. So, the difference is very high. Okay, now we shall come into that thing that MB systems are equipped with in situ diagnostic and analytical capabilities during the growth. You see that in this figure I have shown you that mass spectrometer is there and read is there. You see this is mass spectrometer and that is read. So, now we shall come into those aspects of the MB growth, that two important equipments are or accessories are there in the MB system attachments are there. One attachment is the quadruple mass spectrometer or residual gas analyzer, gives information regarding the ambient in the growth chamber at all times. Ambient in the growth chamber means the chemical composition gases inside the growth chambers. So, that means if you want to know the carrier concentration, if you want to know the chemical composition, whether it will be aluminum 0.3 or 0.38 that I have mentioned, it will be analyzed by the mass spectrometer or the gas analyzer. It is in situ. Another is the reflection high energy electron diffraction, or in short it is known as REED, RHEED, reflection high energy electron diffraction system. It gives insight to the growth mechanism and surface reconstructions. Okay. It is basically related to the surface morphology. Reed pattern is formed by the elastic scattering of electrons from the periodic crystal lattice. When the epitaxial layer is grown, it is single crystal layer if it is epitaxy. So, from the periodic potential, if it is a crystalline structure, then what should be the potential of the crystal structure? Periodic potential. It will be periodic potential because periodicity is maintained in the single crystal. So, the electrons are scattered from the periodic potential. Okay. So, that elastic scattering of electrons from the periodic crystal lattice, that pattern is given by the Reed. The grazing angle of the electron beam is shallow, very small, some theta degree, 2 degree, 5 degree, 10 degree grazing angle of the electron beam. It implies that it penetrates the uppermost layer of the crystal only. It is not the normal incidence. Normal incidence means it is 90 degree. So, if it is a normal incidence, it penetrates deep inside the bulk, but grazing angle means it is confined to the topmost layers or the surface layer only, that is the grazing angle, and it penetrates only the uppermost layers of the crystal. Diffraction basically takes place from the first layer because of the grazing incidence. It will not penetrate deep inside the material, only 1 or 2 layers will be scanned. Reed pattern shows streaks, not spots. Streaks means narrow band of light. Streaks, this type of streaks will be there, not spot. Okay. From the Reed, many things you can learn, many things you can understand of the growth. Sensitive to surface changes, either due to structural changes or due to adsorption. When there is a change in the adsorption pattern, that means the chemical composition will be changed. To calibrate growth rates, you can calibrate growth rates. Observe removal of oxides from the surface. calibrate the substrate temperature, monitor the arrangement of the surface atoms, determine the proper arsenic overpressure, because when gallium arsenide grown, arsenic overpressure must be there, because even at 480 degree centigrade growth temperature, arsenic will evaporate from the substrate surface. So, it must be grown using arsenic overpressure. Give feedback on surface morphology, provide information about growth kinetics. So, all these 7 important aspects of the growth can be monitored using this read spectroscopy. That is very important. You see that point number 2 is observe removal of oxides from the surface. What is this? Observe removal of oxides from the surface. What is this? What is that removal of oxides? Because you see that when we grow something, when we take the substrate or the wafer, obviously there must be an oxide layers on it, that I have mentioned. And why there is an oxide layer? Because of the dangling bonds. Unsaturated bonds are there because of the abrupt termination of the crystal. Because when we talk about an wafer of a substrate, basically it is a piece from the bulk crystal. So, when you cut a portion of it, that bond is terminated. Say this is a bond. So, you break here. So, it is terminated. So, it becomes like this. So, this surface, this is unsaturated bond, on this surface there is unsaturated bond. So, there on the both the pieces there will be unsaturated bonds, that is known as the dangling bonds. Dangling bonds, and dangling bonds are very prone to oxygen. Even trace amount of oxygen, if it gets, yes, the surface become oxidized because of the dangling bonds. So, that oxygen or the oxide layer from the substrate, be it silicon or gallium arsenide or indium phosphide, that oxygen layer or oxide layers can be removed. Before the growth it must be removed. Before the growth it must be removed. You can remove it by etching, that is chemical. That is chemical etching. Some acid treatment you can use to etch the oxide layer, but there can be dry etching also. Using MB, dry etching can be possible. Dry etching can be possible means high temperature baking. What is baking? What is baking? Where the baking is used? Yes, for the preparation of cakes, not fabrication. Cake cannot be fabricated. So, at high temperature baking, you can bake the substrate at high temperature to remove the oxide, or you can use some inert gas ions, because you see it is a high vacuum system. So, you can use argon or that type of inert gas, make it ion, and then bombardment of the substrate. So, due to the bombardment of the substrate by the chemically inert ions, oxides will be removed or etched. So, that removal of oxides from the surface. Okay. So, now how to remove the oxide? You see that native oxides can be decomposed, and it can remove the other process by one is evaporation. High temperature baking. Okay. One is high temperature baking, so that the native oxides or the other things can be evaporated. It is by the method of evaporation. If you bake it, it will evaporate, and pressure is very ultra high vacuum is there. So, it will go away as soon as it will be evaporated, it will go away. So, one is the high temperature baking. Another approach is to use a low energy ion beam of an inert gas. To sputter, clean the surface. To use a low energy ion beam of an inert gas to sputter clean the surface. Remember that when we sputter something, whatever be the energy, I have written that it is a low energy. So, there will be deformation of the surface. So, that means we have to make some low temperature annealing that we have mentioned during our discussion on diffusion and ion implantation. You can remember that during our discussion on diffusion and ion implantation, we have used that term. It must be followed by low temperature annealing. Okay. What is the job of this annealing? To rearrange, to reconstruct the crystal lattice disorder, because when there will be some sputtering or implantation, so the substrate will be deformed, some crystal damage will be there. To make it ordered, there will be some low temperature annealing. Okay, that is very important thing. And generally for RHEED, RHEED, 3 to 100 keV high energy beam, electron beam is directed with a small angle, grazing angle to the substrate surface. You see, this is that incident electron beam, this is the sample. So, it is grazing angle diffraction, and this is that you see that the screen, phosphor screen, where the sticks are obtained. This is the sticks 1, 2, 3, 4, 5, these sticks are obtained. So, there is a monitor or a screen which is attached to the MB system to see the screen, to see the structure or the surface of the sample, and you see that sharp RHEED patterns are obtained when atomically flat surface is there. If your substrate, if your epitaxial layer is atomically flat, then sharp RHEED patterns will be there. If rougher surface is there, then diffused RHEED pattern will be there. And layer by layer growth mode, if there is more than one layer, say super lattice, many layers are there, quantum well, many multi quantum wells, many layers are there, layer by layer growth, then you will get RHEED oscillations, and from the frequency of the oscillations you can determine the thickness of the layers. You see, these are the streak patterns. Number 1, this is diffraction pattern from ideal smooth surface. Okay. Here you see diffraction of real smooth surface, this is some broadening is there, it is almost spot or dot like of things, the spots. Here it is a streak type of spots, and if it is a 3D cluster, not layer, only clusters are formed, then the streaks will follow this type of a pattern. And if it is a polycrystalline, not a single crystal substrate, a substance or epitaxial growth, then this pattern will be like this. So, from the pattern of this read, you can infer that how your how your epitaxial layer looks like. Yes.
Basically, one streak is implies only single layer, one layer.
Yeah. One streak is
One streak reflects only single layer.
basically it's the grazing angle is so you see that the angle is so low that the streaks are from the layers only. Okay. Then if you can consider different kinds of layers, say in this case you see that oscillations will be there. This is layer A, layer B, layer C, layer D, layer E. So, first in A layer there is nothing, it is basically the substrate. So, at this point you see the point A. Then some island types of growths are there, B, nucleation. Then this is the point B. Then more nucleation sites are there, it is point C. Then some of the nucleation sites formed a layer type of growth, D. Then a full layer is formed, E. So, from the oscillations of the reed pattern, you can conclude the different layers. How many layers are there? You can infer about the layer composition, the layer thickness. So, there is simulation software which can be read with this read intensity oscillations. So, different types of at different stages you can evaluate the condition of your subs. No, it is not very easy process, but everything is computer controlled. So, basically computer takes this data and they give you on the screen that the surface is smooth. Okay. Now, if you investigate something very theoretically or say very radically, then that is a separate story, but for normal cases these are basically used for optimization. One, a process is optimized, then you need not to see those pattern or any kind of thing. It is for the optimization only. As soon as it is optimized, everything is redundant. You need not to follow those things. Okay. So, there are many oscillations type of thing, and using this oscillation type you can oscillation frequency corresponds to the monolayer growth rate. So, from the frequency you can see how many monolayers have grown, etc. So, that is not very easy process obviously, but for optimization you have to follow that path. Here you see that when we talk about the substrate and the layer, so there is no guarantee that all the time your epitaxial layer will have the same lattice constant like your substrate, because not available always. Say zinc oxide is one material for which the substrate is not available. The lattice constant of zinc oxide does not matches with any other normal semiconductor substrate, because substrate is available only in the form of silicon, germanium, gallium arsenide, indium phosphide, sapphire, gallium phosphide, etc. Only these type of substrates are available commercially with good chemical composition and free from any defects, dislocation, etc. For zinc oxide you cannot use any of them, because one thing is that zinc oxide is an is a Wurtzite structure. These are or cubic or zinc blende structure except sapphire. Sapphire you can use, but the lattice constant of sapphire is not exactly matching with zinc oxide. But how you can grow? You have to use a substrate. So, people use either silicon or sapphire type of thing, and there will be lattice mismatch. You see that the lattice mismatch is given by delta A by A, it is equals to A minus A 0 by A. What is A? A is lattice constant of epi layer, that means epitaxial layer, and A 0 is lattice constant of substrate. Okay, it is A0 is lattice constant of substrate and A is lattice constant of epitaxial layer. So, A minus A0 by A is given by the it gives the lattice mismatch. It is a parameter to describe the lattice mismatch. Okay, lattice mismatch. Now, if A equals to A0, A and A0 are same, then there is no mismatch, perfectly matching, no mismatch. When A greater than A0, when A greater than A0, see this is the case. In this case you see that this is substrate. So, substrate is A0 and this is the epitaxial layer, it is A greater than A0. Then what will happen? You see that it is basically so far as the parallel constants are concerned, they are forced to shrink. Here it is, you see that laterally they are larger than the substrate, but as you grow the layer you find that laterally the epitaxial layer is shrinked, there is a shrinkage laterally. Okay. Perpendicularly it has increased, but laterally it is shrink. That means it is strain, it is a strained layer and this strained layer is basically the compressive strain, because the strain can be compressive, it can be tensile. The strain can be compressive, the strain can be tensile. So, this is, you see that in this case it is a strained layer. Here also you see that the substrate crystal has lattice constant less than the epitaxial layer. Here you see what happened. Here vertically they have what you see? You see that at the boundary between the substrate and the epitaxial layer, there is a dislocation type of thing or disorder type of thing, but on the rest of the cases it is perfectly matching. You see that the top layers are matching. So, that is unstrained layer. That layer is known as the pseudomorphic layer. As the layer starts growing, there will be a competition between the strain energy and the chemical energy. Strain energy because of the elasticity. The strain energy comes from the elasticity, because they are difference lattice constant. So, there will be elastic strain energy. So, there will be a competition between the elastic strain energy and the chemical energy. Okay. And there will be one concept which is known as the critical thickness, which is determined by Hc, critical layer thickness. Critical layer thickness of whom? Critical layer thickness of the epitaxial layer. This critical layer thickness, it arises due to competition between strain energy and chemical energy. Okay. It arises due to competition between strain energy and chemical energy. For less than critical layer thickness, for less than critical layer thickness, that means less than Hc. for less than Hc, minimum energy is achieved by strain. Okay. For less than critical layer thickness, minimum energy achieved by strain. For greater than Hc, that means if it is larger than the critical layer thickness, dislocation is formed. Dislocation is formed. So, we can say that less than the critical layer thickness, there will be no strain, okay? There will be no dislocation, and it is very small. Okay? It may be some order of nanometer, 4 nanometer, 3 nanometer, and growing that nanometer is very difficult in any system. Okay? So, that is very important concept, that if the lattice matching is not there, then there will be two possibility. One is that the thickness of the epitaxial layer may be greater than or less than the critical layer thickness. Okay, there is a formula for critical layer thickness. I am not going into those details. Critical layer thickness, if the grown epitaxial layer is higher than the critical layer thickness. Suppose I am considering one case of, say, A is one substrate and I want to grow B on it. Okay. For A and B system, say critical layer thickness is, say, x angstrom. For A B system, the critical layer thickness is x angstrom. Then if the thickness of B is less than x angstrom, it is free from any defect or dislocation. That is known as pseudomorphic layer. For B less than x angstrom, it is pseudomorphic layer. That means unstrained, there will be no strain, there will be no dislocation. Good device you can build over that. If B greater than x angstrom, strained layer will be there. That means dislocation will be there. Okay, so for any system, A B system, A is one material, B is another material, you have to consider what is the critical layer thickness if the lattice matching is not there. If it is matched, you need not to bother about, but if it is not matching, then try to keep it below the critical layer thickness, or if it is larger than the critical layer thickness, think that there will be dislocation and strained layer, it is known as the strained layer. Okay. And the pseudomorphic layer is not a strained layer, it is unstrained layer. Okay, thank you.